Welcome to Chemistry Lab. Today's lab, electrochemistry. Electrochemistry is the last big topic in Chem 1146, and we got a whole lab devoted to it. Good times. We have already looked at redox reactions at the beginning of the semester. Remember the acronym oil rig, right? Oxidation is loss of electrons, reduction is gain of electrons. A redox reaction is nothing more than the species being oxidized, passing electrons to the species being reduced. It's a transfer of electrons. It's a special type of reaction. And a battery is nothing more than separating the site of oxidation from the site of reduction so that you force electrons to travel from the site of oxidation to the site of reduction. Sometimes our acronym will have an oil rig in front of it to kind of help us recognize that we describe the anode as the site of oxidation and the cathode as the site of reduction. So what we're going to do today is look at the electrochemistry reactions between different metals. You're going to have a collection of different metals at the front of the lab, and we're going to measure the voltage difference between them. Voltage is a potential energy difference between the site of oxidation and the site of reduction. And we're going to be measuring the voltage in terms of an E cell, right? And a positive value for an E cell means a spontaneous reaction. That just means that it occurs once you hook them together. A negative value would indicate a non-spontaneous reaction, meaning that it's a reaction that will not occur unless it has outside energy provided to it. All of the reactions that we're doing in the first part of the lab are spontaneous reactions. So if you actually measure a negative E cell whenever you measure the voltage on the voltage probes, that just means that you have the leads backward and you need to switch them, because all of these should be spontaneous reactions. We're going to use a lemon as a salt bridge, a connector between the metals and our site of oxidation and a site of reduction. And we've got a bunch of different metals that you're going to be putting together and then attaching voltage probes to them and measuring the voltage. We're going to compare the measured voltage to the theoretical voltage. In other words, we're going to look at these E cell values that you measure and compare them to the theoretical ones. The theoretical values can be determined from the reduction potential table. In that table, all of the reactions are half reactions showing reduction only. Let me use as an example zinc and copper, because those are the first two metals that you're using in the experiment. In the reduction table, reduction potential table, zinc is shown being reduced. Reduction is gain of electrons. So we're looking at zinc ions picking up 2 electrons to form zinc metal. The reduction potential that's given for that is a negative 0.76 volts. Copper is also in this table, a little further down. Copper ions pick up 2 electrons to form copper metal. And the reduction potential given here is a positive 0.34 volts. Now, when we hook up zinc and copper, we can measure a positive E cell, but one of these metals is being oxidized and the other one's being reduced. The question is which one? Which one's being oxidized and which one's being reduced? The reduction potential table shows everything as a reduction. So what we want to do is manipulate these numbers and determine which direction will give us a positive E cell value. We can think of the E cell as the reduction potential plus the opposite sign here for the oxidation potential. Let me write that. In other words, if the reduction potential for zinc is written this way, right? This is written as reduction. Flip it around, and that would be oxidation, and we would also change the sign here, right? So we want to pick the combination that will give us a positive E cell, and that combination is going to be this one. If zinc stays reduced like this, and if copper stays reduced like this and zinc is oxidized, that would give us positive values for both of these so that when we add them together, we get a positive number. In other words, for the reduction, let's keep copper ions picking up 2 electrons to form copper metal. And let's look at the oxidation of zinc, which would be the reverse. Zinc yields zinc ions plus 2 electrons. And so when we calculate the theoretical value for E cell based on these numbers in the table, we come up with 0.34 plus 0.76 equal to 1.1 volts. That's a positive number. That's the spontaneous direction. And that's how we know which metal is being oxidized and which one's being reduced. We're looking for the combination that gives us a positive E cell. Because if you were to reverse all of this, you would have a negative number. And what I'm saying is that for all of these metal combinations that you're using, we should be able to calculate a positive theoretical E cell value, meaning that all of these reactions should be spontaneous. You are looking at these different metal combinations in the lemon cell, and then after that, you'll combine different lemon cells to add these voltages together. For example, if you hook together 3 different lemon cells, you should have 3 times the measured voltage, theoretically. Usually, experimentally, you measure less than what you could theoretically. You will also look at these reactions using vinegar as a salt bridge instead of a lemon, but you should have fairly similar results with that. The very last thing that you're doing in the lab is essentially an electrolytic cell. You're plating a copper penny with zinc. But what you're doing at this very last reaction is looking at a non-spontaneous reaction. Right? I said all these metal combinations that you're using should be spontaneous, but the very last experiment that you do, the very last part is labeled an electrolytic reaction, and that one is non-spontaneous, but we can make it go anyway. Remember, non-spontaneous just means that it doesn't go by itself. But if you hook it up to a battery, we've got a bunch of 9-volt batteries in the lab, then you can make it go anyway. I believe that's all you need. Have a great lab.